since there's 4 variables, the bottom 2 sections of the vectors are 1 and 0 and 0 and 1.
Yes.
Which reveal that let's call it x3 and x4 are free variables.
Yes.
So that you can put those into that, and then you can work backwards from that to get A.
Well, not A, but the reduced row echelon form of A, right?
Yes.
You have to be a little bit. You have no idea what A is, right? But
yeah, of course.
Reduced row echelon form.
It could be anything.
Yeah. I mean, yeah. So that's essentially right? I mean, what you just said is basically it, right? So yeah. suppose you had a a reduced row echelon form. Let me just say, and that those variables are 3 and 4. So let's just go ahead and do it like that. So let's say that I had. So it'd be like this, right? 0, 1. So it'd be like that, right? And then it's 3 by 4. So 0, 0. Sorry, I got to think. Let's see. And then I had like a 3 here and a 2 here, right? I don't know, and something like this, right? I could do something like that. Okay, so that's sort of, that would be a reduced row echelon form of A, right? So in reduced row echelon form, these have to both be 1s. All right. Now your book, we've sort of been through this. Your book defines echelon form as needing 1s here. I don't really know why they do that. It's kind of weird, but reduced row echelon form does need 1s here, right? But from this point, right, we can read off the solutions. I mean, if you just think about it once, right? First of all, you do have these 2 free variables there, right? So let's just call this one S and T, right? So the usual thing is to say like, let x3 be some arbitrary S, right? Let x4 be some arbitrary t, right? So you're sort of parameterizing the solutions, right?
Is that kind of parameterization required for the exam, or is it fine to leave it as like x3, x4?
It's okay. I mean, if you look at, I mean, in the end, well, I mean, let's sort of work through it and then we'll see why. I mean, there's kind of a reason not to do that, because then you're kind of treating x3 and x4 as somehow different from x1 and x2. And you kind of want to consider the vector x1, x2, x3, x4 as just sort of an arbitrary vector in null space, and you want that parameterized in terms of 2 variables, right? So it's a little weird to use the x3 and x4 there. I mean, it's a little hard to see now, right? But when we sort of finish working this out, we'll see why that's true, right? Yeah. But we're going to see here, right, that what we're going to get is x1 is equal to minus 2s minus t, right? So we see we just put minus signs in front of those things, right? So we're gonna, we're gonna have minus 2, so right, we're gonna have minus 2s, right? Because I called that s, right? So basically I'm gonna have an s here, plus, and I'm gonna have a t here, right? And then minus 1 t coming from that, right? And then minus 3, right? And then minus 4 there. Sorry, there should be a t there. And then here, s is going to go, so this is x3, right? So I have a 1 and then a 0, and then I'll have 0 and a 1, right? So we can read off our basis vectors for null space by just looking at this matrix, right? We sort of, okay, look there and just negate those signs, right? So we just take that minus 2 and minus 3, right? We take that minus 1 and minus 4. And then what do we do for the rest? So here we just have our free variables, right? So the first one is just x3, and so we get that 1, 0. And that's kind of what you were thinking, right? And the 0, 1, right? So once you have the reduced row echelon form, it's really kind of trivial to get the basis for null space. You can just read it off from the matrix, right? So, that's what I'm asking you to do there, is basically to go backwards, right? Given the basis for null space, just turn that around and read off what the reduced row echelon form has to be, right? That's the idea, right? Now this, I could have said 4 by 4, right? I mean, there could be another row of zeros here, and then you'd have to do something a little bit different, right? But still basically the same, right? So we'll forget this now. Now again, since these are in R4, right, the number of columns have to be 4, right? That there's no choice about that. Okay. Now the reason for the notation, right, because in the end you want to say like an arbitrary. Sorry, I'm not good at writing on these little.
No, it's all right. We're all adapting.
So you sort of want to say that like your arbitrary element, right, of null space, right, is going to be written like, it's supposed to be an s. Minus 2. What I wish they had is one that like corrected my handwriting as I went. That would be nice. All right, plus t, all right, times -1 -4 0 1. Okay, that's hard to read. Anyway, there you go. Right. So I mean, this is kind of the idea, right? We want to say an arbitrary element of our null space is this sort of sort of an arbitrary linear combination of those two vectors, right? Okay. It would be a little weird here to write, right? If I, I mean, this just looks a little strange. If I call this green, if I call this like x3, right, and x4.
Just for the reason that it kind of looks like it's defining itself.
Yeah, I mean, you're sort of treating this, I mean, this is supposed to be just an abstract vector, right, in our space, right? And I'm wanting to define it somehow, and it's a little weird to look at it like this and say define it in terms of x3 and x4, right? Like, suppose this weren't 4 dimensions, suppose this were 3 dimensions, right? I don't know. Suppose we just had something like this, right? And then I have my let me put the S and T back, right? S T, right? So this is now describing some sort of thing in 3 space, right? So in R3, I mean, in fact, it's defining a plane, right? Because it's a linear combination of 2 variables, right? But if you wanted to say take a computer and graph it, right, or draw it, right, you would use a parameterization like this, right? You'd say, okay, let S be some like a bunch of points in between, say, -10 and 10, and let T be a bunch of points between -10 and 10, right? And then sort of draw the corresponding things that you get for all those points, right? I don't know if you've ever drawn anything on a computer. That's sort of how you do it. You have to parameterize in terms of these things, right? So you're sort of you're saying, okay, draw these arbitrary things parameterized in this sense, right? So in some sense, you're saying, well, x1, as a function of S and T is, whatever, right? -2S minus T, right? And then x2 in terms of S and T, right, is, -3S minus T, right? And then x3, right? So, I mean, you've got all these 3 variables that are really parameterized in terms of S and T, right? So it would be weird to say x3 of, I don't know, x3 and x4, right? Or something like that, right? That's sort of what you end up doing this way. Anyway, I mean, it's just sort of not good notation, right? And the language you use in math is a really powerful language. It's good to have good notation. It's kind of bad to have bad notation, right? Because then you just end up confusing things. So there is a reason, right? It really is better to say, let x3 be an arbitrary thing, let x4 be an arbitrary thing, right? And then you parameterize all 4 variables in terms of that S and T, right? Is really what you're doing, right? I don't know if that makes sense, but think about it some. I think you'll agree after a while. Yeah. Right. Okay. But anyway, I mean, so long answer to your question, right? What this problem basically asks you to do is take, now this particular basis I chose here happens to be such that you can sort of read off the reduced or echelon form easily, right? So here's a question for your brain now. Suppose I give you just a basis, right? Suppose it weren't so nice, right? I just gave you a basis, right? So maybe that's a thing to do. Let me clear this. I think what I did is I changed the amount of I've got this pad thing I'm writing on, right? Which is not the screen, right? So I'm writing in one place and looking somewhere else. And I shrunk the region I'm using, and I think I shrunk it too small, so it's like too sensitive to my hand movements or something. Suppose I said, okay, the null space is given by these guys. Hopefully what I write down is okay, fine. So I'll just say those 2 guys, right? So the NSA equals, well, okay, span, sorry, I didn't leave myself room of, these two guys. In fact, let me not put let me put all 1. So I don't even have that 0 there, right? Right, and now I said, okay, find the reduced or echelon form matrix of A, right? So find our REFA. Okay. So, well, now you can't read it off of those 2 vectors very well, right? But we know how to reduce these two bases into a nicer basis, right? So I could just, put these two things into a matrix, right? And I can just start doing row reduction, right? So I can subtract off 2 of that first thing, right? So then you get 1, 1, 1, 1. And and again, and I'm saying this again, it's supposed to be a 3x4 matrix, right? So that's, same sort of setup, right? And so here I have 0, 1, 0, 2, right? Or my 2. So, and now this isn't, so this isn't quite reduced row echelon form, right? Oh, sorry, that's not even what I care about. What I care about here is just getting a basis that's in the right form. So I will get this in reduced row echelon form. So now I'm going to take row 1 and subtract off 1 row 2 so that I sort of kill off that 1 that's up there, right? So I get 1, 0, 1 minus, 1, 0, 1 minus 1, right? And then 0, 1, 0, 2, right? Okay, so now, right, so I know that this is really the same as the span of those two things, which is now 1, 0, 1 minus 1, right? And 0, 1, 0, 2, right? Like that, right? And now you can play that same kind of game. Now you've got the ones here and here. I mean, it's a little bit weird because I've got the little sort of little identity matrix in the wrong place in some sense. But you could say, okay, those are going to be the 2 free variables, right? And these will be the rest of the matrix, right? So you can. Okay, maybe okay. I didn't think of this through. Okay, so sorry. Let me back up. Let me try one more time. Okay. I really want the 0, 1. So usually when we do this, we get our little sort of identity matrix toward the left, right? Let's try to do this backwards, right? Let's do some row reduction to try to get it on this side instead, right? So let me subtract off 4 of row 1. Let me see. Let me subtract. Now I'll still do 2. So I'll still do this first step. Sorry, you'll see what I'm doing in just a second. So then I get 0, 1, 0, 2. Okay, and then let me get rid of that 2 right there. Oh wait, no, that's not what I do. I see, I get myself in trouble. Sorry. Okay, I'm doing this on the fly. So let me try one more time.
It's understandable.
This is why I didn't give you the problem like this, because I hadn't really thought through it carefully. Okay, let me subtract off 4. So I'm going to just sort of work backwards, like doing row reduction, but usually we start across that way and down. And I'm going to do it backwards. I'm going to start across that way and down. So I'm going to do it backwards like that, right? So 1, 1, 1. I'm going to subtract off 4 of row 1. So then I end up with -2, -1, -2, and 0, right? So I got rid of that. Okay. And then what I want to do is get rid of that 1 there, right? Yeah, that's what. So okay, then I'm going to divide by 2, I guess, divide by minus. Let me divide by -2 there. Okay, so then I get 1 over 2. So I'm going to get some fractions here, 1 and 0, right? And then I'm going to subtract up to get rid of that 1, right? So let me give myself some more room. Okay, so then I'm going to get, now when I subtract up, I'm going to end up with a 0. I'm going to end up with a half and a 0 and a 1 and 1 and 1/2 and 1 and 0. There we go. Okay, so this is more like what I wanted, right? So now my null space of A is really the span of those two guys, right? I mean, these are clearly linearly independent, right? Because of the way the 0s and the 1s are in there, and we haven't changed the span. We haven't changed the span because we're just doing row operations, right? So these are all linear combinations of each other, right? So that's the same argument as we usually do. The only thing I'm doing different here is I'm sort of doing the Gaussian elimination kind of backwards. I'm sort of working in that direction instead of the other direction because I want this little sort of identity matrix over on this side, right? And then I can arrange these things like this. I have my vector 1, 1/2, 1, 0, right, is one of my vectors, and the other vector is now 0, 1/2, 0, 1, right? Okay, and now we can get our reduced row echelon form. So now you've got the same sort of thing as before, right? You sort of have there, there's your x4 is going to be a free variable, x1 is x3 is going to be a free variable, right? And then you have these, the other parts of the matrix that's going to be there, right? So now we could read off our reduced row echelon form matrix. What we know, there's going to be a row of zeros down there, right? And then we know here I'm going to have minus a half. Let's see. So sorry. Then I'm going to have here 1, 0, 0, 1. Okay, that's going to be there. And then I'm going to have minus 1. Minus a half. All right, and that was a 1. Sorry, my handwriting's so bad. And then here I have just 0 stays a 0, and then I have minus a half. Right, so I just changed the sign of those things. Sorry, 0. Yeah, okay. All right, but basically I'm just changing the signs of those guys. All right, and putting them into that column. Right, doing the same thing there. So I mean, that's what we. Whoops. I'm not sure how it does that. Stop. I guess I erased the first thing, right? But we're sort of, again, we're just kind of undoing what we would do if we had this reduced row echelon form. How would we read off the basis? Well, that's exactly what we would do, right? If I were to take this as my reduced row echelon form and read off a basis for null space, I would get exactly these two vectors, right?
Mm-hmm.
You'll have to rewrite it in your own handwriting to see it well, right? But that's the idea.
Yeah.
Okay, so you could start off with any two vectors here at all that form a basis for null space. And so now think about this. Given any two vectors as a basis for null space, I can play around with them for a little bit and then reconstruct the reduced row echelon form of A, right? Mm-hmm. Okay, so that should completely tell you how to do this other direction, right? So, now you want to go, now you want to work this direction, right? Going from right to left, right? Because if you know that null space A is equal to null space B, what can you tell me about a basis for null space A and a basis for null space B?
I'm sorry, say that again.
If you know that null space A equals null space B, what can you tell me about a basis for null space A and a basis for null space B?
Shouldn't they be equal?
So they don't have to be equal, but you can definitely pick a basis that is equal, right?
Mm-hmm.
Right, and then you can manipulate it the way I just showed above, right? And from that you can reconstruct the reduced row echelon form, right? So you just got to sort of turn that into a proof, right? I mean, it's kind of constructive, right? What you've done, I mean, what we've done is we've seen how to take a basis for the null space of a matrix, and from that basis, not from any information about the matrix itself, but just from the basis of the null space, compute the reduced row echelon form of the matrix, right? So we just discussed how to do, right?
Ugh.
So we'll think about that, right? I mean, that's what we just went through, right? That's exactly what we just did.
Yeah.
Right. So that pretty much tells you how to do that one, right? You have to process it some and then figure out how to write it down, right? But that's basically,
yeah, it's just trying to juggle all of it at once, but you also can't put it in like an exemplary form with actual numbers. You have to use the like AB notation to try and generalize it.
well, I mean, you do have to do some things, right? I mean, you need to describe how to, I mean, yeah, okay, so I mean, I see what you're saying. You do have to do some things in that way, right? You don't actually do anything in particular. You don't do any manipulations, right? But you can, I mean, basically the point is you can pick a, so you know that the null space A equals the null space of B.
Like, so
right?
You're saying for the majority of this proof, I don't have to explicitly do much computation other than just explaining.
You have to explain things. Yeah, I mean, that's true usually with I mean, not always, but often with theoretical things, right? You need to say that this is going to be the span of a couple of vectors that, basically have this form A, B, 1, 0, C, D. I mean, so there's that sort of abstract thing, right? 0, 1, but we know we can always sort of get the basis into that form, right? Now it's not true that we can always get it into exactly this form. I mean, you might have to do something a little different where the where the free, I mean, so here I'm sort of choosing the free variables to be an x3 and x4, right? I mean, the two free variables may be an x2 and x3, right? Or
So
something like that.
couldn't you just replace that with saying, like, you could give that example, but then have a note that says that the free variable, you can always reduce it to get the free variables somewhere, and it may not explicitly be this. Or
That's
do you have
basic.
to?
Yeah, that's basically the idea. I mean, somewhere you have the free variables. There's going to be two free variables. You know that, right? So basically somewhere in your basis, you can sort of, I mean, you see the main point is there's this little identity matrix embedded in there somewhere, right?
Yeah.
And then you have this other stuff. So basically you have this little thing that's a little identity matrix that comes from the two free variables. And then you've got this other stuff that is telling you how to reconstruct the reduced row echelon form, right? Yeah, but it could occur in a different way. I mean, you could end up with an A1, B0. I mean, even if it turned out to be like this, right? And what C, what do I want here? 0, D, 1, right? I mean, so now it's kind of interleaved like that, right? But you still have the little kind of identity matrix stuck in there that's going to be giving you, and you can always do, you can always get it to that form. And why can you always get it to that form? Well, so that's because you can always row reduce, as long as the two matrices, as long as the two vectors are independent, right? You're always going to be able to row reduce your two vectors into something that has, into a echelon form or an REF form, right? So this is a different from the REF of A, right? This is so suppose my two basis vectors were A1 through A4, right? And B1 through B4, right? So so I have that, right? So now I take those two vectors and I put them here, and B1 through B4. So you don't actually do any computation, but there I've got those things, right? I know I can always row reduce this thing so that I end up with a reduced row echelon form. So it may look like this, and then some things. 0, 1, CD, right? I mean, it may look like that, right? But it may look like this too. It may look like 0, 1, A, B, 0, 0, 1, C or something. Actually, that doesn't have enough free variables. So actually, I guess the way we are here, since we have two free variables, this is the only thing that can happen, right? That's, when we do that, that's sort of the only thing that can happen. Right. So you can always sort of get your basis for null space into this form. And then once you have it in this form, you know how to reconstruct the reduced row echelon form, right? Of A.
Yeah.
That's the point.
And like it said on there, it actually returns that the reduced row echelon form of A is equal to reduced row echelon form of B.
Well, I mean, the logic, what is the logic? Tell me exactly what the logic is. All we know is that the null space A is the null space of B, right? So tell me exactly what the logic is.
So the logic working all the way from the beginning is that the null space, both of them, you can take their basis and always reduce them to get a sort of identity matrix so that you can always get back to a reduced row echelon form.
Yes.
For both.
Yes. And the same, right, the way you reduce those two vectors will be the same, because you can always pick the same basis for null space A and null space B, right?
And that's just one of the given definitions that we have to use for the it's
not really a definition.
The fact that null spaces can be represented, I mean, okay, since on this side of the equation, we're taking the null space of A and the null space of B as a given. And since they are the same, they can possibly have the same basis. And thus we can reduce their bases the same way to get the same reduced row echelon form.
That's right. Yeah.
Okay.
Yeah, and I guess I've been a little sloppy here because I don't actually say anything about the dimension of these, right? So I've been pretending in what I've been writing that the dimension is 2, right? But the dimension of these could be 1, and the dimension of these could be 3 or 4, right? I mean, you actually got a few options for what the dimension of this could be, right? So you could, instead of having 2 vectors, you could have one. You could have, well, I guess the null space of A could be trivial, right? so that there's no basis vector, right? And then it could have dimension 1 because we know that this is a subset of R4 because A is a 3x4 matrix, right? So the null space is going to be a subset of R4, right? So we know that, right? So these spaces could have dimension 0, 1, 2, 3, or 4, right? So you've sort of got those options there, right? But you don't have to go through those options one by one. You just sort of have to say null space of A is equal to null space of B, so we can pick a basis for both, right? We can reduce that basis into a form that sort of has this embedded identity matrix. Now that embedded identity matrix may be I3, or the example I just did, it was I2, right? It could be I4. I mean, it could be any of those things, right? But you basically have this embedded identity matrix, and once you have that, you can sort of reverse engineer the reduced row echelon form, right? You don't have to write out all the cases and explain how to do that. You just have to explain clearly that it can be done, right? And that finishes the proof for us.
Yeah, that makes it a bit less daunting.
Yeah. I mean, you always get to do things like that when, like, it's really hard. I guess one thing about teaching this online is I mean, okay, I have to say, when you teach it in class, it's also very hard. Proofs are hard. Proofs are hard for people to get, right? And it's very hard to get students to focus on the right things, right? So for example, in this last topic for DQ2, right? I wanted everyone to produce for me the matrix for the linear transformation with respect to the standard basis vector, and then use that for part B, right? That's what I asked in the homework. So basically no one did that. Not a single person did that. What lots of people did were do some individual little manipulations for part B over and over again, the very same manipulation over and over, right? Without realizing you're duplicating work here, right? You should just do this once and be done with it. That's the whole point, right? But then when you do, and you may have done this too, right? You have this matrix and then you're multiplying it by this vector. But then when you do that, you write out, I'm not saying you, I'm saying you, like the class. I don't remember if you did it or not, right? You write out all the little, how did the matrix multiplication go, right? Like, like you have this matrix and you're multiplying by a vector, and then you write down the first element of the multiplication as 0 plus 2 plus 4 or something like that, right? And you sort of have these 3 rows. So you're putting in that detail, which is really, really irrelevant, right? So you know what I mean? It's hard to get people to focus on the right thing. Like, like before, we've had to do some stuff where you had to do some stuff with inverses, right? And a lot of effort was put forward to compute the inverses for some reason, right? Which is really not the interesting part of that argument, right? So it's always hard to get people to do what you want them to do in these cases, right? But anyway, I think you know what to do here. I think you know how to proceed.
Okay. Yeah, could I see the whiteboard real quick?
Yeah, as sloppy as it is.
Yeah. I mean, if anything, it's got meaning in it.
Somewhere. It's got some information content of some sort. Okay, so quiz 3. So this problem, okay. Yep. Okay, so yeah, what is your question?
So that the operator pi, that just means the sum of the product, or it's just the products, right?
That's the product, yeah. So this is a great big product of n minus 1, right? So when you look at this, right, this particular term is linear, right? Because this is a constant, right? This is x minus a constant, right? So this term that, can I highlight it just it or not? Maybe not. Come on, mouse, let go. How do I get my mouse to let go? Okay, there we go. Right. Maybe I can't highlight it, but this term right there is just a linear term, right? 1 power of x, right?
Right.
Okay, and so how many am I multiplying together? I'm multiplying n minus 1 because I'm leaving out the case I equals j, right? And so this whole thing, when I multiply it all together, is an n minus 1st degree polynomial, right? And that's where it's supposed to be, right?
Right.
Okay. So yeah, so that's what that means. Just the product of all these things. Okay. So now what?
So I was like, the formula on the right side of the pi symbol just confused me a lot. Like I didn't know what CJ and CI we're supposed to be?
Well, it says right here, right? They're distinct reals. That's all, right? There's some distinct reals.
Okay.
That's all you know about them, right? So for every collection of distinct reals, I get a different basis, right? That's
Right.
what you're getting here.
Okay. So then, how are we to get or draw the conclusion that when I equals j, it's 1, and if I does not equal j, it's 0?
Well, so yeah, well, when you plug in Cj, right? So pretend I isn't j, right? And let's plug in Cj, right? So what does this term right here become? What does the jth term of this product become? It becomes Cj minus Cj, right?
Oh, yeah.
Which is 0, right? And then these are always distinct, right? Because these are distinct reals, right? Ci minus Cj is never 0 itself, right? So we're never dividing by 0,
Okay.
right? So if we take any j other than I, right, and we put in Cj here, one of the terms is 0, but then we're taking this big product, and so 0 times anything is 0, right? So it's going to be 0, right?
Right.
And if I is equal to j, if we plug in that, right? Sorry, if I is equal to j, then we get 0. Sorry, if I is equal to j, and I do pi, yeah, sorry, I've got to be careful about where I'm using my i's and j's here. So now I'm doing pi of ci, right? That's what I'm saying, right? If I is equal to j, so I'm looking at pi of ci, right? Because I is equal to j, I'm in that case. So then this term right here becomes, well, in fact, all these terms, right, become ci minus cj over ci minus cj, right? So they all are 1.
Right.
Right? So they all become 1s. You just got a big product of 1s, 1 times 1 times 1 times 1, and minus 1 times, right? And so that gives you 1, right? So that's why that's true. Okay, so that explains this, right?
Yep.
Okay, and now what? So go on.
That makes more sense. I was just so confused on the CJ and CI.
So does that explain the rest of it then? Does it make sense? Does the rest make sense?
Just for film base. Yeah, that makes more sense now.
I mean, the fun thing about this is if I fix your C1 through Cn, right? And we have our basis here, right? And I take any arbitrary polynomial at all, right? Anything at all, right?
Right.
And I want to know how to write it out in terms of the PIs, right? So I'm fixing these. I'm fixing the C1 through Cn, right? When I do that, that fixes these PIs, right?
Yeah.
Okay. And so now I want to take an arbitrary polynomial and write it, expand it in this basis, right? But it's completely trivial to do. I just have to evaluate P at each one of those points, right? And then multiply by Pi, right? So it becomes really easy to take an arbitrary polynomial P, an n minus 1 degree polynomial, and write it out in terms of that basis, right? So here's the sort of representation in terms of that basis. And all I have to do is take that P and evaluate it at each of the CIs, right?
Okay. Yeah.
So that turns out to be a really useful, that makes it very easy. So, you give me n many points on the line, right? And an arbitrary polynomial, right? And I can sort of rebuild that arbitrary polynomial in terms of these specific n minus 1 basis polynomials, right?
Okay.
So this, it's a well-known theorem, maybe. I mean, maybe it should be well-known, right? If you give me n distinct points from a polynomial, you give me n distinct points on the real line, right? And an n minus 1 degree polynomial, right? Then let me try this again. If you give me n many points in the plane, okay, but where the x coordinates are different, right? Distinct, right? So think of those as being the CIs, right? Then there is a unique n minus 1 degree polynomial going exactly through those n minus 1 many points, right? And this tells you exactly how to create that polynomial, right? Because I just, you give me those n many points in the plane, and I take their x coordinates and say the x coordinates are C1 through Cn. Those are the x coordinates, right?
Right.
And I define these basis polynomials, these PIs here, right? And then I just take the corresponding y coordinates, and you call those y1 through yn, right? And I just put them here, y1, y2 through yn, right? And expand it out in terms of that basis. And that gives me that n minus 1 degree polynomial that goes through exactly those points, right?
Okay.
So this gives me a really easy way of coming up with polynomials going through a specific set of n minus 1 points. It's a nice little application. You don't, I guess in some sense, you don't actually use it. It's useful for your sort of sanity. I mean, just assume part A is true, right? Don't worry about whether or not you've proved it or not, okay? But from this that that if I have two reduced row echelon form matrices, right, and I know that they have the same null space, then I actually know that the two matrices are the same, right? And so that just helps your sanity up here and knowing that whatever you get from this will actually be correct, right? Because I'm telling you to compute exactly the reduced row echelon form of A, right? So you might say, well, maybe if I take two different bases here or something, I can produce two different, because there's a specific thing you're going to produce. You're going to take these two vectors, right? And you're going to produce a 3x4 reduced row echelon form matrix, right? So you're going to take these two vectors and produce that thing. Now you might have in your mind, okay, maybe if I took two different vectors that sort of still had this form, but still gave me a basis for the null space of A, maybe I would get a different reduced row echelon form, right? And so you may be worried about that. Like, how do I know I got the right thing here, right? But part A of the theoretic one basically says that doesn't happen, right? If given that you can reconstruct a reduced row echelon form from these two vectors, it is the unique one. That sort of follows from that part A.
How we were supposed to do topic 4 DQ2, because I thought I had done what you had asked, but I didn't.
Yeah. Okay, so yeah, I mean but you did, and I don't actually remember exactly what you did, but what almost everyone did is the same. So I'll assume this is what you did, right? You did the following. You got the first part right. So you got the matrix for L with respect to the basis B, right? Correct. And then what you did is you took, so in the next part they gave you just a vector in R3, right?
Yes.
And then what you did is you transformed it into a vector. You transformed, this basically the standard basis representation of that vector, say 1, 2, 3, whatever it is, right? You took that vector and then transformed it into the base B representation, right? And then you applied the matrix to get L of that, and the output is also in the base B representation, right? And then afterwards, right, you retransform that base B representation back into the standard form representation of the vector in R3, the output, right? So I mean, maybe I should turn on or pull up this little thing. Right? Here, let me clear this. Right. So you got a matrix that basically. So in my notation, I would tend to write L of B, because you could have, two different bases, right? I have an L going from V to M, this is sort of the general setting, right? And I could have a basis B for that one. I could have a basis C for that one, right? And then, and I could, have, and then, so this would be like the representation with respect to those two bases, right? One for the, what we call the codomain, right? Where stuff is originating from. And then, sorry, the domain and then the codomain, right? So the domain where stuff is originating from and then where it's going to, right? So like that. Okay, so now in your case, it's a little bit more specific, right? So we could have the same V on both sides. So that's sort of your case. Now we could still have two different bases, and so you'd still write that, right? But even more specifically, now in your case, you have a single basis, right? And so when these two guys are the same, instead of writing the B comma C, we usually just write B, right? So now we have the base B representation of L, right? Okay, and then you would take vector like, I don't know, 2, 3, 4, something like that, right? And then you would, and now this is just in R3, right? So this is kind of the standard basis representation of itself, right? You know,
Yeah.
it's always kind of hard to figure out what you mean by that. It's like saying 11 is the base 10 representation of 11. It's, you know, you're so used to using it, it's a little hard to say what you're doing, but you know, this is sort of, you know, there is a vector in the Platonic world, you know, out there, whatever that means. It happens to have this representation, sorry, for with respect to the standard basis, which I usually write as E, right? And for some reason I use these calligraphic, you know, squiggly things for basis, right?
Yeah.
Okay, so you know, there's sort of this unknown weird vector object that lives out in some sort of space of mathematical objects, and we represent it in the standard basis this way, right? But that's kind of not how we usually think about things. We just usually think of that's the vector, right? That's how we usually say stuff, right?
Yeah.
I don't know, if you do lots of physics, you'll get more used to doing that kind of thing, right? But then what you did is you converted it. You took this and said, okay, fine, this actually has the representation something, you know, I'm just going to make something up. I mean, not use 1 minus 1, 1. Okay, n base b, right? I mean, that's not correct for whatever the problem is, right? I'm just making it up, right?
Yeah.
But that's basically what you did, right? Got that. And then you applied this matrix to that. So you said, okay, fine, I get L of b, and then, so, you know, again, this is the vector x, right? This is the vector x, right? So I take my vector x with respect to the b basis, that's this thing here, right? And what I get out when I'm done is I get L of x, which is what you want to write down, right? But you get it with respect to the b basis still, because that's what your matrix did. That's what this matrix did, right? It took something in the b basis and put it out in the b basis, right?
Yeah.
So then what you do is you take this thing, right? And you say, okay, now let's go back and figure out what L of x is in the standard basis, right? Which we usually just write as L of x, right? We don't usually write, again, we sort of like here, I kind of left off that notation, right? But usually we just call this L of x, right?
Yeah.
So like, what are you doing? You're taking x, right? You're sort of converting it to, you know, xb in the b basis, right? And then you're converting that to L of x b, right? Because you're applying that matrix. So here we do LB. That's how we get that one, right? And then you're taking that and you're converting that to L of x in the standard basis, right? So what are we doing here? We're doing a transformation from standard basis to base b to b, right? And over here, what are we doing? We're doing a transformation from base b to base e to basis e, right? So these are both transformation matrices, right?
Yeah.
Okay, so, you know, call this one, this is the one that's easy to write down. Call this one T, right? And this is just doing the opposite. This is T inverse, right?
Yep.
Okay, so what I'm interested in you doing is writing down what is the matrix of L with respect to the standard basis, right? And so that's going to be, you know, T and then your LB and then T inverse, right? So, right. So you want to compute that matrix, right? That's what I asked you to do. Compute that matrix. Compute the matrix of L with respect to the standard basis, right? So that is what I actually asked you to do, right? And then when you want to solve this problem up here, well, then you just take LE, which is the representation with respect to the standard basis, and multiply by, what did I call it? 2, 3, 4, right? 2, 3, 4, and you're done, right? You don't do, you get an answer out, right? Whatever it is. All right. So what all of you guys did is you did this transformation. You said, like, you know, I'm going to take each x I'm given, I'm going to do this thing, I'm going to apply the matrix, and I'm going to transform it back again, right? And you just kept doing that over and over again, right? Well, really what you want to do is you want to do that once, encode it in a matrix, and then for each of these 3 problems, you just take that matrix and multiply it by the thing you were given and get the output, right? So that's what I wanted to see you do, right? I wanted to really see you use the change of basis matrix on both sides of this thing to get the representation with respect to the standard basis, and then just use that matrix for all three of those parts, right?
So like the matrix that was found in part A.
Well, the matrix that was found in part A is right there, right?
Mm-hmm.
Okay, so what are these other two? So we got you know, I've got my base B going to E. So I can't remember. Let me see if we can remember what B is. Maybe you guys can remember. So it was one of them was 1, 1, 1. One of them was what, 1, 1, 0. Is the order right?
Yeah,
Have this happen?
I think so.
One of them, what's going on with my pen? Sorry, my pen's doing something weird. I'm not sure what it's doing. What was the other one? 1, 0, 0.
Yeah, I think 1, 0, 0.
I don't know what my pen is doing something weird. I'm not sure what it's doing. Huh, that's weird. I'm not sure why it's doing that. Oh, I may have to restart this thing. Okay, so right, suppose it's that. Well, what is the transformation matrix where I'm going from, dang it. Okay, sorry, I may have to restart this thing. It's doing something weird. So I'm trying to get the transformation matrix going from base B to base E. So given that I have this basis, how do I write down that transformation matrix? This is the easy direction.
Isn't it just like those vectors in a matrix?
Yeah, in the columns, right?
Yeah.
Yeah. So I'm gonna have to restart this. Sorry, I'm not sure what it's doing. I'm not sure if it's the writing pad or the whiteboard. Let me see if I can get it to work. But yeah, you're right. When you're going from a basis to the standard basis, you just literally write down the vectors, right? So it's as simple as it gets, right? You can't get any simpler than that, right? So yeah, so the matrix T, no, it's still doing this. Shoot. The matrix T is just equal to not sure why it's doing this. 1, 1, 0. Okay. The order is important here. I don't remember if these are in that order or if these are even correct, right? So you want to make sure you get that correct, right? You want to keep them in the same order they were in, but you do just write them down as the columns.
Right.
Right. Not the rows. I mean, you may be tricked here into thinking we're writing down as the rows, but these are going in as the columns, right? Right. And then T inverse, which is doing the transformation in the other way. So it's going from the standard basis to the base B basis, right? Is literally just the inverse of that matrix. So you just compute the inverse. That's T inverse, right?
Yeah.
Okay. And then the matrix, how that works. Then the matrix you want is right here, right? The matrix you want is actually just, because what are you actually doing? And this is what you guys did, right? You went from the standard basis to the base B, right? But that's T inverse, right? That's what that does, right? And then you applied the matrix LB, right? So there's that LB, right? And then you took the result and went from base B back to standard basis, right? So that's T again, right? So the matrix that does that all at once, the representation of L with respect to the standard basis, is just this thing, right? You take T inverse, you take this product, right? T inverse. I mean, I guess I would say at T times the representation of L with respect to B, and then times T inverse, right? The order in which you're doing things is kind of the other way. You're kind of going in this side and out the other side, right? So you're sort of applying T inverse first, then you're applying the transformation, then you're applying T, right? And that's literally what everyone in the class did, right? You sort of did these 3 steps. You computed this thing, right? You applied that matrix, and then you computed this thing, right? Does that make sense?
I can't hear anything.
Oh, can you not hear me?
Yeah, Professor.
Can you hear me now? Huh, okay, that's weird.
The last 2 are BC.
Okay.
Can you hear me?
Yeah, we can hear you.
Hey, sorry, I don't know. My internet went out, but it came back on all of a sudden. Sorry about that. Maybe that's what was,
welcome back.
yeah, maybe that's what was causing it. But anyway, you see, did you get that? I mean, so, you know, we have our transformation matrix, right? Which is taking me from base B to the standard basis, right? T inverse takes me from the standard basis to base B, right? And so what you guys were all doing was doing that sort of by hand, right? You were doing this part by hand, right? Then you were applying this matrix. That's still slow for some reason.
Hey, could you share your screen?
Oh, am I not sharing my screen again? Ah, okay, I see. Sorry, I'm sitting here playing. Yeah, I guess it messed up all sorts of things. Okay, let's try this again. All right, sorry about that. Now you can see, hopefully.
Yeah.
Right. Right. Okay. So yeah. So this thing, right? This thing. So this is just our transformation matrix from base B to standard basis, and you just write down the vectors as the columns, right? This is now the transformation matrix from the standard basis to base B, right? Okay. So what this whole thing here is the transformation matrix. I mean, this is now the matrix for L with respect to the standard basis, right? You take something with respect to the standard basis and put it in on this side, right? You transform it to base B, you apply this matrix you got, right? The output is then in base B, and then you transform it back into base E, right? So that gives you the matrix for L with respect to the standard basis, right?
Yeah.
So applying this one matrix to this X gives you the result all in one step instead of having to go through these steps, right? So you're not repeating these 3 steps every time. You're just applying this matrix to X, right? And that's what I wanted to see you guys do, right? Does that
makes sense.
Okay.
Could you, I don't know, like I understand what you're saying, but it'll be hard for me to apply that with real numbers and stuff.
No, it's not. I mean, we've got it, right? You've got this matrix. Everyone did this right. Although I think the reason people gave, you know, I caught like halfway through when I was grading, I was saying that this was right, but sometimes for the wrong reason, which is a little worrisome. But I think everyone got the right matrix here. So I think both of you got the right matrix here, right? You both know how to do this, right? This is just the matrix, you know, where you take the vectors that you're given. Again, you want to double check that these are the correct vectors, right? And you stick them in there as the columns, right? And then you take the inverse, you know how to do that. You can even use MATLAB or something if you want to take the inverse of this matrix, right? So you get that. And then you just multiply them together, right? You know, you're just, you know, each one of these is an operation, right? But what happens when you compose linear operation? I mean, maybe this is something that's worth saying here. When you compose linear operations, what do you do with the corresponding matrices is you multiply them, right? So you know, I take my arbitrary X. I'm afraid to write on this thing because it seems to still be sticky. Okay, there. I take my arbitrary X, right? I feed it into this matrix. What's it hit first? Well, it hits T inverse. So what's that going to do? It converts it to base. It takes this and base. This is my, you know, vector and, you know, R3, right? Standard basis, right? And it's going to convert it to base B for me, right? So you don't have to go and solve that silly system. You just throw it into this matrix and it converts it to base B, right? Then you apply the result, you know, you apply L to that in terms of that base, right? So you just apply this matrix and you get the result, which is now L of X, but in base B, right? But you want the result in the standard basis. So now you got to convert back to the standard basis. So you feed that result into T, right? So the result of doing those 3 things is just what you get when you multiply these 3 matrices together. You get this single matrix, which I can then just multiply by X and I get the result, right? I get L of X in terms of the standard basis. Does that make sense?
Yeah.
Right. And so, yeah, I mean, doing it is trivial. You write down the matrix, you know, just put the things in columns, right? You take the inverse, right? And you just do that with whatever, you know, either do it by hand or, you know, I would do it with MATLAB at this point, right? And then multiply the 3 matrices together. And again, you can do that in MATLAB if you want. Because like I was telling Spencer earlier, I don't care to see you do that, right? That's not what's important anymore, right? What's important is knowing how to construct this matrix here. That's important, right? Knowing how to multiply matrices is no longer important. You know how to do that. You can use MATLAB as far as I'm concerned, right?
Right, and then the L with respect to B, is that what we get from multiplying?
No. You got that. That's the one you got, right? That's, you know, you were given something, right? You were given something like, L of y1. Yeah, I don't know if the internet's still sticky, but for some reason this board is still sticky. It's not working well. But you guys, I just can't get it to work. You got something like, I've got to do something else. Let me see. For some reason this still isn't working. I'm not sure where the slowdown is. Hold on just a second. I'm getting. So you know what? Can I? Let me try the annotate thing here. Let me see if I can just do my own annotation. Okay. Let me just bring up something blank to draw on. Okay, sorry. Yeah. let me try this again. Let me bring up just a blank nothing to mess on. What am I trying to do? Take a Word document. Fine. Just open up a Word document. Maybe the heat is causing problems here. I don't know. Okay, let me see if this works. So, okay, let me turn the annotate back on and see if I can just scribble on this. Okay. Let's see. Yeah, you were given something like L of, sorry, Y. L of Y1 is equal to, and I don't remember what it was, but it's like maybe C1 Y1 plus C2 Y2.
Oh, yeah.
Right, plus C3 Y3 or something like that. Actually, were there things like this, or maybe it was like 1, 2, and 3. I don't remember. Maybe it was 1, 1, and 1. Yeah, maybe it was just like, okay, maybe it was like this. L of Y1 is equal to Y1 plus Y. I'm gonna make something up that's hoping this is something right? Y3, right? Something like that. Yeah. And L of Y2 is equal to, say, I don't know, Y1 minus Y3. I'm just gonna make some stuff up, okay? And L of Y3 is equal to, let's say, Y2 plus 2Y3. Okay, I'm just making up some stuff. I don't actually remember what the things were, right?
Yeah, and then we got a matrix from that.
Yeah. Now what people did was they kind of did this wrong, right? So you do want to be careful. So now I want to write down the matrix with respect to basis B, right? And so basically what I'm going to write that down is I'm going to compute L of Y1, and I want to write the result with respect to the basis B. That's going to be my first column, right? And then I'm going to write down L of Y2 with respect to the basis B. And L of
your columns there are just the vectors, right? So like L of Y1 would be column 1, right?
Yeah. So well, not L of Y1. That's whatever sort of strange Platonic object it is, but the representation with respect to this basis, right, is that, right? So what is the representation L of Y1 with respect to B is, well, now this is respect to the B basis, but it's got 1 Y1, 1 Y2, and I think I meant this to be a plus, right? So this would be just 1, 1, 1, right? Right, and so L of Y2, the way I've got it would be 1, 0, minus 1, right? And L of Y3, the way I've got it would be 0, 1, 2, right? So in this particular case, the matrix I would get here would be 1, 1, 1. So notice you're building this in columns, not in rows, right? And this one would be 1, 0, minus 1. And this one would be 0, 1, 2.
Right.
Okay. Right. So now what does this matrix here let me do? Well, it lets me it lets me take something in with respect to this basis, right? So if I'm given something as a linear combination of Y1, Y2, and Y3, right, then I can apply that representation. So if I take an arbitrary X, which is in, it's in R3, right? But I've got it represented with respect to this basis, Y1, Y2, Y3, right? And so I take that representation with respect to B, right? And so this is just a column vector with 3 entries, right? It'd be like C1, C2, C3 here, right? So forget this thing. Let's just say this is X, right? So there's my X, right? Some linear combination of Y1, Y2, Y3, right? So this would be like C1, C2, C3, right? And then when I apply this matrix to it, and the result you get out will be another column vector, right? But what it'll be is it'll be the result of L of X written with respect to the basis B, right? So now everything's in basis B, right? So that's what you get out from that operation, right? And this matrix right here is the matrix L of B. Oh, I don't know how to erase. Let's see. Okay, sorry, I'm not used to this board. Okay, let's try this again. Where's my drawing? How do I draw? Is it format? No, that's not right. Sorry, I'm used to using this. Spotlight, erase. Do I just turn it off? How do I get? Oh, draw. Sorry, there we go. Draw. Okay. All right. Change back to draw. Ooh, I want to draw. Oh, I have to pick a draw. Okay. I'll get this sooner or later. Right? No, I don't want that. Probably squiggly line. Thank you. Oh my gosh. Okay, so this matrix right there is the matrix LB, right? That is the matrix with respect to the basis B, right? You feed it in something with respect to the matrix to the basis B, right? You apply the matrix to it, and the output you get is the result of L of X, but written out in terms of the basis B, right?
Right.
So that is that matrix. Let me see. Did I kill that? I guess I killed that other thing, right? So I want you to do this. So right now I want the matrix of L with respect to the standard basis, which I call script E, right? That's what I want, right? And so to get that, you had to just sort of combine these things together. You had this T, you had this L B, and you had this T inverse, right? And so this T in this case would just be these vectors written as the columns, right? Because that's the transformation matrix that takes base B representations to standard base representations, right? And this is the inverse. It takes standard representations to base B representations, right? So now I just take my standard representation, whatever, 1, 2, 3, all right? And standard bases, right? And I feed it in there, right? And T inverse is going to turn it into a base B representation, right? This matrix L of B, that one right there, right? Will then tell me L of this thing, but with respect to the base B representation, right? And then I apply T to it, and it's going to turn it back into the standard basis. So it'll just, the final result of this thing will just be L of X, but with respect to the standard basis, right? That's what this one's going to do, right? But this is a product of three 3x3 matrices. So the result is just a 3x3 matrix, right?
And then that's what you get L with respect to the standard basis.
Yeah.
And
So I
then
mean,
that for each problem that gives you the vector.
yeah, then you just take this matrix and multiply it by that vector, and you get the result. There's no more intermediate steps because those intermediate steps are now encoded in the matrix, right?
Right.
The steps everyone did are sitting. This is the part you did when you changed the vector they gave you into the base B representation, right? Then you applied your matrix, right? And you got something out, right? But that's now a base B representation. You had to retransform that back into the standard base representation. And so that was applying this T. Right? Or maybe people didn't do that. I mean, I didn't look that carefully because people weren't doing what I wanted. So I sort of stopped looking and said, I want this done instead. Right?
Yeah.
Yeah, so I mean, just go fix that. But it's a good lesson. I mean, you want to learn how to do this. You want to learn how to use the matrices to do. I mean, think of what you're doing as a process, right? You're doing this, and then you're doing that, and you're doing this other thing, right? You don't want to do those separately. You certainly don't want to do them by hand. You want to encode all of that into a matrix that just does it, right? That's what you want to do, right? This is important. I mean, say you use linear algebra for computer graphics or something in the future, right? You want to show something moving, and you want it to stretch a certain amount, rotate a certain amount, stretch a certain amount back this other way, and do these other things, right? And if you're doing the same kind of operations over and over, you don't want to do those as 3 or 4 or 1,500 separate operations. You just want to multiply all the matrices together and do it once, right? It'll save you a lot of, say, CPU time or GPU time or something, right? So
Right.
that's, yeah, you want to think of matrices, you want to stop thinking of matrices as just arrays of numbers and start thinking of them as transformations. They're doing something, right? It's a good sort of way of thinking about things.
Okay.
Good.
Makes
Anything
sense.
else from either of you?
I don't think I have anything right now.
Okay, cool. So I will maybe talk to you guys later. Good. So good luck finishing up the exam, I guess. That's
Do you have to head out?
I don't have to. I mean, I don't want to spend too much longer because I do need to do other stuff, but I can do a little bit more.
Okay. Yeah, because I did want to talk about the thoughts that I had about the second part of the proofs.
Okay. Oh, and who am I talking to now? Sorry.
Spencer.
Spencer, okay. So we talked about this one. So
Yeah.
not this one, right?
The next one. Because I'm just trying, well, first of all, I could not find where you did this in your notes, the part under the remark, where you were showing
it's definitely in the text, and I'll show you where I did it in the notes. It's a long section, so people probably skipped it because it looks long and hairy, so it's easy to skip. And it actually came up in the DQs before, so let me find it here. It was where we were doing, must be topic 2.
Yeah, I think that one's simpler than it looks.
This one's not hard. Yeah, you just have to, I mean, you get to use these results here, right? So right here, we were doing all this stuff where I'm trying to show, I'm actually in the middle of trying to prove that the product of a determinant is the determinant of the, sorry, the determinant of a product is the product of the determinants, right? And so in doing all that, there's this thing about a sequence of elementary matrices, and okay, so right here, right? Let A be invertible, then A is similar to I. So that means A is row reducible to I. So that would be like that squiggle sub row thing that I have there. Right? And that means that I is equal to E multiplied by A, where what E is a bunch of row operations, right? Because what we're saying here is A similar to I means I can row reduce A to I, right? And so what that means is I can apply a bunch of these elementary matrices one after another, because each one is doing a step in the row reduction, right? And so I is equal to E times A, where it's a product of these elementary matrices, right? Okay. Yeah, okay, and then the point here is that is it all, this product is invertible, right? Because we also had an exercise like that. So, say this is a type 1 row operation here, right? So we know the inverse is actually also a type 1 elementary row operation, right? So we know that each elementary row operation, we look at its inverse, is equivalent to an elementary matrix, is an elementary matrix of exactly the same type, right? Okay, so I can invert this E, and basically what happens, you just invert all these pieces and flip the order, right? Okay, so then what you get is you get that E is equal to A inverse, right? Because basically we get E, I is equal to E times A, so E is equal to A inverse, right? That means that A is equal to E inverse, so that means A is also equal to the product of a bunch of elementary matrices, right? So what this theorem tells me is it tells me that an invertible matrix, so when you sort of parse all that through, right, is that any invertible matrix is just the product of elementary matrices, right? In other words, it just comes from doing row operations to the identity matrix. That's exactly what every invertible matrix is, right? Okay, so that's giving you the relationship, right, between, right? So if I have A is reducible to B, what that means is I can come up with a sequence of elementary matrices, right? So that when I apply them to B, I get A, right? Or vice versa. I mean, I could apply it to A and get B. Either way, it doesn't matter, right? So think of this E as encoding a sequence of row operations, right? And you know that that's invertible because each of those individual steps is invertible. And so to invert the whole sequence, you just flip the order and invert all the pieces, right? So that's all this says. So this E, in fact, I'm using the letter E to sort of hint that. So it's not an elementary matrix, but it's a product of elementary matrices, right? It's just coding. Again, I'm sort of talking about matrices as coding operations, right? So it's coding a sequence of row operations, right? Okay. So yeah, so you know that from that stuff. Yeah, I mean, actually, you don't need all the stuff I was just pointing at. You really just need that, right? So again, let me just say this simpler, right? A is a row equivalent to B, just means I can get from A to B by a sequence of row operations, right?
Yeah.
So now turn that around. That also means I can get from B to A by a sequence of row operations, okay? So I just do that, right? I take B and I apply a sequence of row operations and get to A, right? And I just code that sequence of row operations as a matrix, right? And it's going to be an invertible matrix. So I know that this holds if and only if that holds, right? So we know that that's equivalent, right? And then you can use what we've done above, right? I mean, so you can always use what you've already done, right? Here. Because you know that if A and B are row equivalent, I mean, this is something you know in chapter 1. What do you not change? I mean, what was the whole point of doing row operations? You don't change the solutions to the system of equations, right?
Yeah.
Right. So if A and B are row equivalent, then it's definitely the case that A of x equals 0 if and only B of x equals 0. Right. So they have the same null space. Right. So given A, using A, B is actually almost trivial. Because
so basically you can postulate the fact that since they're row equivalent, they'll have the same solution and have the same null space.
They have the same null space.
Since they have the same null space, you can use your answer from before to postulate that you can arrive at the same reduced row echelon form for both A and B.
Yeah, not the answer, but just the fact, right? You're going to use the fact.
Yeah.
You're going to use this boxed thing right there, right?
Yeah. Okay. That makes more sense. Okay. All right. And if you have to go, you have to go, but
let's see, I'm trying to say, let's see, I told you this here. I feel like I changed some. I've made a couple of additions. Where did I do it? I guess I did it up in the true false. Yeah, you may want to look at the new version. I made sure I put this definition of this sort of circle plus thing. We call it O plus in math, but that kind of thing. All right. And I guess that comes in down here. Where was that? It comes in down here again, right? So I give that definition again down here. Okay.
And that's just basically asking to prove that the combination of the null space of A and the row space of A is all of Rn, correct?
It's a little bit more. I mean, it also says that their that their intersection is trivial, right? The intersection is just the 0 vector, right? But that's equivalent to saying that. So I mean, you can think of this when you say V is equal to U plus W. It just means you add all the things in U and all the things in W, and you get all the stuff in V, right? So that's what this is saying, right?
Yeah.
But there may be lots of ways. So given a particular V here, right, there may be lots of ways of adding a U and a W to get V, right? So the additional thing here is that like when the intersection of the two spaces is just trivial, right, is that there's a unique way, right? So if I take V and I decompose it into U plus W, that's a unique decomposition, right? So there's only one way of doing it, right?
And so that's only present when the intersection is the 0 vector.
Yeah, they're equivalent. I mean, that's a good exercise to do too, right? It's a good exercise to see that that's equivalent. So saying that there's a unique way of, so there's a way, right? When I say V is equal to U plus W, you know that for every V in V, there's some way of writing V as a sum of things in U and things in W, right? Show that, just do the argument yourself that to see that this condition here that U intersect W is the trivial space is exactly the same as saying there's a unique way of doing this, right? So those turn out to just be the same thing, right?
Yeah.
So yeah, you're saying a little bit more here. You're not just saying that everything in Rn is a sum of stuff here, but you're saying that it's a unique sum of stuff there.
Okay.
Right. And later on we'll actually show that these are yeah, later on we'll actually show that these are not only unique, but these are orthogonal to each other. Right.
Mhm.
In fact, you're in week 5 now, so you may actually see this as an exercise that these two spaces are orthogonal to each other. So in other words, every vector here is actually perpendicular to every vector there, which is a much stronger thing, right, than just saying that they're. So I mean, that certainly implies that the zero vector is the only thing in both, right? Because I can't have two non-zero vectors that are orthogonal to each other, right? I mean, I can't. I mean, not in the same, like, I can't have a single vector. Let me put it like this: if I had a single vector in U and W, right, and that single vector was orthogonal to itself, right, the only way that can happen is if it's the zero vector, right?
Mhm.
But you're not using that here. You're just going to show that they don't have a non-trivial intersection, right?
Okay.
So it's not completely trivial. It's not too hard. You can use theorems in the book, right? I mean, you might need to use some of the counting theorems and stuff about basis and stuff like that.
Mhm.
Dimension of null space and row space and column space and stuff like that, right?
All right.
Yep. Any other questions?
I don't have any.
Okay.
Yeah.
This one, I would say this one's the hardest one. So I'm going to let you
Really?
play with that.
Okay.
This one is the most theoretical one. So yeah, I think the rest are, I mean, so if I were to rank these, so this one's harder than the other 3 except that last one. But this one, you're going to kind of use what you did up here. You're going to kind of use that, right? By the way, if you guys, I know some of you guys do chat with other people, so don't give away everything, but feel free to share that information, right? That what you'll use to prove this direction, the hard direction, right, going from this side to that side, right, will be basically the same as what you used up here to reconstruct the reduced to echelon form, right?
Yeah.
And then B follows from A almost trivially, so that's a thing you can share. Then what I said here isn't secret, so you can say whatever you want to there. This one's the one that's harder, so I'm going to leave that to. Sorry, someone's at the door. I'm going to leave that. I'm going to leave that one to sort of separate the full score A's from the others.
Yeah.
So.
All right.
Yep. Cool.
Yeah.
Cool.
If it's not too much, could I get the video?
Yeah, sure. Okay. Yeah. So I will. Are both of you okay with that? Do either of you care if the other one has it? Okay. So I'll just put it up as a private video on YouTube, and I'll send you to the link.
All right.
Is that okay?
Thank you.
All right.
Thank you.
All right. Yep. Talk to you guys later.
Yep.
Mhm.
Bye-bye.